Good afternoon. I'm Kenneth Slowick, Curator of Musical Instruments at the National Museum of American History. On behalf of the Smithsonian Distinguished Scholar Selection Committee, which is comprised of previous winners of the Smithsonian Distinguished Scholar Award, I am pleased to welcome you to this ceremony and lecture by the Smithsonian Astrophysical Observatory's Dr. William Forman, the 2020 recipient of that honor in the sciences. The Smithsonian Distinguished Scholar Award was originally entitled the Smithsonian Secretary's Distinguished Research Lecture Award and has been given 20 times since its inception in the year 2000. Nominations are made by peers of those nominated and must be supported by letters from outside academic adjudicators, plus complete listings of the nominees' scholarly output. The Smithsonian Distinguished Scholar Award highlights the institution's commitment to knowledge derived through historical inquiry, the scientific method, rigorous analysis and peer review, and the syntheses that can result from a broad understanding of a particular culture or period. People around the world trust the Smithsonian to care for America's treasures and to pursue and share historical, cultural, and scientific truth. Because of that trust, it's important that we uphold our founding principles and advance James Smithson's mandate to increase and diffuse knowledge. To further these long-standing institutional commitments, in 2017, Secretary David Skorton added a second annual Distinguished Scholar Award so that each year sustained achievement at the Smithsonian in both the sciences and the humanities is acknowledged. These two awards, together with the Secretary's Research Prizes and the Research Tent at the annual staff picnic, offer Smithsonian employees, members of Congress, and the public several opportunities each year to learn about the remarkable work that takes place at the institution. These events each showcase Smithsonian scholars in the new and innovative ways they are sharing knowledge with the world. The criteria for the Distinguished Scholar Award are, first, outstanding and sustained achievement in research. Next, long-standing commitment to the Smithsonian. And third, and no less important, the ability to communicate to both a specialist and a non-specialist audience. I'd like to thank the members of the selection committee who were active in this round's advisory review process. Louise Court of the Freer-Sackler Gallery, David Dvorkin of the Air and Space Museum, Bert Drake from the Environmental Research Center, Giovanni Fazio of the Smithsonian Astrophysical Observatory, Adrian Kepler of the Natural History Museum, Nancy Knowlton, who has worked both at the Tropical Research Institute in Panama and the Natural History Museum, Christine Mullen-Kramer of the National Museum of African Art, Igor Krupnik of Natural History, Ellen Miles of the National Portrait Gallery, Michael Neufeld of Air and Space, Douglas Owsley of Natural History, and Tom Waters of NASM's Center for Earth and Planetary Studies. To review the nominations, I think my fellow committee members will agree, is both an enlightening and a rather humbling experience. Enlightening in that one learns, at least in a broad sense, of many research projects, some quite long-spanning, which illustrate the breadth and diversity of our collective mission of contributing to the increase and diffusion of knowledge. And humbling because each one of the nominees is obviously an important figure in his or her field, and we are honored to work beside such distinguished colleagues who, through their efforts, uphold the Smithsonian's deserved reputation for excellence. Before we hear Dr. Forman's presentation today, which is entitled Galaxy Clusters, the Largest Collapsed Objects in the Universe, Born to be X-ray Sources, Secretary Lonnie Bunch has some observations on the special importance of research at the Smithsonian in these perilous times.
Thank you, Ken, for organizing this program and for your leadership as a scholar throughout the year. And I appreciate the work of the committee in selecting today's distinguished scholar, Dr. William Forman. It is a true pleasure to join you today to celebrate Smithsonian scholarship. I want to be brief because I know we all are excited to hear Dr. Forman's presentation. But I do want to say a few words about the importance of this award to the Smithsonian and about research more broadly. As a scholar, I know from personal experience how painstaking, deliberate, and time consuming the process has to be to produce truly excellent research. And I can say without a doubt that my own career has been enriched immeasurably by the scholarship of colleagues from across the institution at the National Air and Space Museum, at the National Museum of American History, and at the National Museum of African American History and Culture, and now as secretary. Every step of my career has been guided by the belief that the Smithsonian is at our best when we marry expert scholarship, deep creativity, and rigorous investigation. Research is the engine of what we do at the Smithsonian. It powers our exhibitions, our educational capabilities, and our decision making. Whether we are studying the long-term effects of climate change, measuring the impacts of COVID-19, or gazing up into the solar system, Smithsonian research changes the way we understand our place in the world around us. Our scholarship is an invaluable form of public service to our audiences, our communities, and to our nations. This is especially true right now. Good scholarship matters now more than ever. The past year of this pandemic has made all too clear the tragic consequences of ignoring data. As disregard for facts grow when they contradict beliefs, as citizens and elected officials discount evidence they can see with their own eyes, institutions like ours need to step in. The Smithsonian, especially in our capacity as a research institution, has a responsibility to restore public trust in facts and science. We need to champion the importance of high-quality research and scholarship. Today's ceremony does exactly that. The Distinguished Scholar Award celebrates the strength of scholarship and the impact this work can make, even as we are surrounded by those unwilling to accept inconvenient truths. Exceptional scholarship reminds us to pursue knowledge diligently wherever it leads. Your work is an expression of our innate need as humans to seek, to explore, to find light in the darkness. Dr. Forman's work embodies the highest standards of Smithsonian scholarship. His pioneering research expands the realm of human understanding. Bill not only leads the high-energy astrophysics division at SAO, he is committed to ensuring that his work reaches and informs public audiences. This scholarship is a shining example of the knowledge that the Smithsonian brings into the world. And I know that I am not alone in saying how proud I am to have Dr. Bill Forman as a colleague. Congratulations, Bill, on this well-deserved honor. Thank you for all that you do.
I'd like to begin by thanking Secretary Bunch. This is truly an honor and a pleasure to be able to join you today to accept the Smithsonian Distinguished Scholar Award. I'd like to also thank the selection committee and its chair, Kenneth Slowick, for his introduction and for shepherding me through the process to prepare this talk. I've spent my entire career here at Smithsonian since I completed my PhD in 1973. And even my PhD studies were supported by Smithsonian Fellowship. My association with Smithsonian dates from 1969, just over 50 years. This has been a remarkable time of discovery, enabled by Smithsonian, the joint Harvard-Smithsonian Center for Astrophysics, and the many friends and colleagues from around the world. I ask you to join me in a 14 billion year journey, starting with the Big Bang to watch the growth and evolution of the largest collapsed objects in the universe, clusters of galaxies. Our universe began almost 14 billion years ago as a very hot and violent place, most likely starting with phenomenal expansion that lasted far less than the blink of an eye, less than 10 to the minus 30th of a second, which is referred to as inflation. After this, the universe continued to expand and cool. At very early times, the dominant elements in our universe, hydrogen and helium, were formed. After about 380,000 years, the hot primordial soup had cooled to about 3,000 degrees Kelvin. At this temperature, The hydrogen nuclei combined with the freely moving electrons, and the cosmic soup became neutral. At this moment, 380,000 years after the Big Bang, these photons from this soup were able to travel freely through the universe, and we detect them today as a microwave background over the entire sky. As the universe continued to expand and cool, we entered the dark ages before the first stars were able to form. The first stars are formed after about 400 million years. Slowly but surely, larger and larger systems formed, galaxies and eventually clusters of galaxies separated from the expansion and the collapse. While the universe as a whole continued expanding, regions where there was more matter than the average felt a stronger attraction of gravity. The matter fell toward these regions of excess density, and as the density contrast grew even larger, so the process accelerated. More and more matter was drawn into these overdense regions to form the collapsed objects we see today, the galaxies and clusters. Afterwards, these systems evolved on their own. The first massive galaxy clusters formed when the universe was about half its present age. Here you see the vertical red line. Cosmically, galaxy clusters are newcomers to our universe. The figure also shows an increase in the expansion rate, an opening of the cylinder here as we come to the present day. This accelerated expansion is driven by the so-called dark energy, whose true nature remains a mystery. The accelerated expansion was only discovered about 20 years ago. If Einstein is correct, and the dark energy is just as described in his equations of general relativity, there will not be much more growth of structure. Clusters will continue to grow slowly, but they may remain the most collapsed objects in the universe. To picture the microwave background, think of looking up at the sky on a cloudy day. We see the bottom surface of the clouds, the surface from which the photons that we see were last scattered, right over here. While we can't see microwaves directly with our eyes, old-style TVs do detect photons from the early universe. In fact, 1% of the static on old TVs was from the cosmic microwave background photons, the oldest photons in the universe. The cosmic background photons are the oldest photons. They've been traveling to us for almost 13.7 billion years, when the universe was only 0.003% of its present age. To appreciate how early this time is in the evolution of the universe, if we scale this time to a human lifetime, it would be the equivalent to the age of a one-day-old baby. At the moment these photons began their journey, their characteristic temperature was about 3,000 degrees. But today, the universe has expanded by a factor of just over 1,000, and the characteristic temperature of these background photons is cooled by the same factor to just under 3 degrees, 2.725 Kelvin to be exact. The figure you see, this beautiful figure, shows the fluctuations in the radiation from the Big Bang that were imprinted at the time of the recombination of hydrogen. These fluctuations are truly tiny, no more than 1/100th of a percent. We see hotter and cooler regions that reflect the underlying distribution of matter, mostly the dark matter. These fluctuations in matter, seen through the microwave background, are the seeds of all the structure that we observe in the universe, the galaxies and galaxy clusters that populate the universe today. Driven by gravity, these fluctuations set the stage for the growth over the next 13.7 billion years. The microwave background, with all its detailed structure, provides incredibly powerful measures of the constituents of our universe. The dark energy here is about 68%. It's an unexpected property of our universe, although Einstein added something like it to his general theory of relativity when it was thought the universe was static. When he learned that the universe was expanding, he thought it his greatest mistake. In the context of general relativity, dark energy is called the cosmological constant and serves to accelerate the expansion of the universe. Dark matter, here in blue, is about 27% of our universe. We see much evidence for its existence. The fluctuations in the microwave background that you've just seen give a precise measure of its contribution to the universe. Most likely, dark matter is some exotic particle that responds with very little interaction with normal matter. But as for all matter, it responds to gravity. In fact, the dark matter is what drives the formation of structure. And finally, there's the ordinary matter here. We usually refer to it as baryons. Everything here on Earth, from ourselves to tables, chairs, the atmosphere, all the elements of the periodic table. The baryons are responsible for the chemistry and the biology. The word baryon comes from the Greek, meaning heavy. Technically, baryons are any particles made from 3 of the fundamental particles called quarks. Putting all the ingredients together and starting from the initial fluctuations defined by the microwave background that you saw in the previous figures, today's computers are able to model the evolution of the universe with ever-improving detail and realistic physics. And here we see the evolution of the dark matter. And I'll say that it's easy, but it's only relatively easy to compute, to model, since it's affected only by gravity. Let's begin the movie. In just a few seconds, you can watch how the almost uniform age, the uniform distribution at an age of about 0.12 billion years, 120 million years old, just 2% of its present age, forms a rich structure of filaments and clumps, today's galaxies and clusters. The first objects to form have the lowest mass, then larger ones arise from both collapse and merging. Gravity alone is at work in the picture you see here to amplify the fluctuations that are revealed in the microwave background. The matter feels the gravitational pull from places where the density of the universe is larger than average. The matter starts falling towards these places and makes the density contrast even larger, so the process accelerates. Eventually, streams of matter coming from different directions collapse, intersect in central regions, forming a collapsed object, which afterward lives on its own. For a galaxy cluster, it takes a good fraction of the age of the universe to collapse. Seeds of even larger structures are present in our universe as well, but they need still longer times to collapse, or they may never collapse. And that is why clusters are referred to as the largest collapsed objects in the universe. The growth is also described as hierarchical because the smaller systems collapse first, and then larger ones. Galaxy clusters are the last to form. You can think of the distribution of objects in the universe seen on the top part of the slide, and their growth, like the growth of cities and towns from small to large on the bottom part of the slide. Very crudely, there are very, very many small stellar systems with a single star like our solar system. Fewer globular clusters with a few 100,000 stars, still fewer galaxies, and very few, perhaps only about 100 of the more massive galaxy clusters in the present day universe. In the real universe, on scales smaller than clusters, the baryons, the normal matter, cools by radiation. This allows these smaller mass systems to condense, become denser, and then to fragment, to break into smaller components. And for these smaller systems, the baryons become dominant rather than the dark matter as in clusters. Hence, our solar system is dominated by normal baryonic matter, not by the dark matter. Galaxies come in 2 flavors. You see 2 examples here. Spirals, M101 here at the top, is supported by rotation. It's like our Milky Way. You see very prominent arms. In the arms especially, there's lots of star formation going on, and that's why the arms are bluish in color from the light from the young stars. These galaxies are generally found in low density environments and mostly avoid rich clusters. Ellipticals, on the other hand, are supported by random motions, and you see a picture of one galaxy here. These galaxies are generally featureless. They're reddish in color. The stars are older, and they're referred to often, these galaxies are often referred to as red and dead because of the red stars and little star formation. On average, these galaxies are more massive than their spiral cousins, and they are the predominant inhabitants of the galaxy clusters. And I've shown you 2 characteristic examples here of a spiral with very beautiful spiral arms and one with none. But in fact, the galaxies come in a continuum from spiral arms to weaker and weaker spiral structures all the way up to through the ellipticals. Looking again from a different point of view, how do the galaxy clusters form? The universe is cooled, the first stars and galaxies have formed. Gravity has been working all along to create these dark matter potential wells, from first small fluctuations, you see a small fluctuation here, to the larger ones. As the universe evolves, the fluctuations collapse, drawing in more and more galaxies and more dark matter and more gas. As I said before, but emphasize again, the region where there's more matter than average feel a stronger attraction of gravity. The matter falls towards these regions of excess density and makes the density contrast even larger. More and more matter is drawn into these overdense regions to form a collapsed object, which afterwards lives on its own. The massive galaxy clusters take roughly half the age of the universe to collapse. This process is the one you see in the schematic drawing. These cross-sectional drawings are described as gravitational potential wells. Like this is a little of a well. You can see a well here and a deeper well over here. You can think of these gravitational wells as digging a hole at the top of a hill and putting in a bunch of marbles at the bottom of the hole. Those marbles will stay trapped in the hole, held by the force of gravity. Only if the marbles are given more energy can they overcome the force of gravity and escape from the hole. In this same way, the gas, the galaxies, and the dark matter are captured and bound together by gravity to form a cluster of galaxies. The gas in these gravitational wells is heated by the work of gravity. In massive clusters, the characteristic temperatures are 50 to 100 million degrees. At 50 million degrees, the gas is about 10,000 times hotter than the photosphere of the sun, the surface of the sun we see. Galaxies clusters are therefore naturally bright in X-rays because of their size and mass. You see over here the expression showing the relationship between temperature T, the mass m, and the size and radius r. The more mass, the higher the temperature. The smaller size, the smaller radius also gives higher temperatures, and clusters are just perfect. They're just the right mass and just the right size, such that the gas that's trapped by gravity has just the right temperature to produce X-rays. Let's look once again at a mature galaxy cluster in today's universe. What's it made of? 85% is dark matter that leads to the formation of the gravitational potential in which the galaxies and hot gas join. There's just a smattering, a few percent consists of stars, and the bulk of the normal baryonic matter is the hot X-ray emitting gas at about 12% of a rich cluster. So again, we see the hot gas directly in the X-ray band, and this X-ray gas has very, very remarkably low density. It's about 1 atom of hydrogen per liter. A volume of this gas, the size of the Earth, would weigh only a mere half as much as a half a teaspoon of water, almost nothing. And yet the volumes in a galaxy cluster are so vast that the gas mass is 4 times more massive than that of all the stars in all the galaxies. X-ray astronomy is a young field. The figure shows the radiation falling from the outside of our atmosphere, from low energy radio waves on the left here, through the familiar optical in the pretty color spectrum here, into the X-rays and the gamma rays. While the radio waves make it all the way to the ground, and there's a perfect window in the optical to which our eyes have evolved to exploit, X-rays are absorbed high in the atmosphere. You can see that over here. Hence, X-ray astronomy had to await the technology of rockets and satellites. We, on the other hand, are almost the exact opposite. We are mostly transparent in X-rays, but totally opaque optically. X-ray astronomy began around 1962 with the detection of the first non-solar X-ray source called SCO-X1 in the constellation Scorpius. The first imaging solar X-ray telescope, you see it over here, was developed a year later in 1963. This solar telescope has about the same diameter and length as Galileo's 1610 telescope. 380 years later, Hubble is about 100 million times more sensitive than Galileo's 1610 telescope. In 37 years, X-ray astronomy achieved a comparable increase in sensitivity with the launch of Chandra in 1999. Chandra was the largest and heaviest payload launched by the shuttle, 22,000 kilograms. It's more than 21 years old now and still going strong. And most incredibly, this huge spacecraft, which was pioneered in X-rays, made pioneering studies and discoveries in X-ray astronomy, is powered with a mere 2,300 watts. While 2,300 watts might seem a lot of watts, it's the equivalent of 1 good hairdryer. Not only do we have to go to space for X-ray studies, but X-rays are notoriously hard to focus, to make real images. If X-rays shine directly on a surface, they're absorbed. Only at very shallow angles can X-rays be reflected. These so-called grazing incidence reflections require exquisite surfaces for the highest angular resolution, and they require large surfaces. As you can see in the figure here, Chandra has 4 sets of mirrors. One set of paraboloids, parabola-shaped mirrors, and another set shaped like the figure of hyperbolas. The focal length, the distance between the mirrors and the X-ray detectors, is about 10 meters, quite large. There are three major missions operating today: the Chandra Observatory, XMM Newton Observatory, and a recent arrival, which was just launched in 2019, called eROSITA, the Spectrum Röntgen Gamma mission, which is a joint collaboration between Germany and Russia. For the Chandra mirror, because the mirrors are all grazing incidence optics, you need this huge area of 20 square meters, which has been coated with iridium to improve the reflectivity. And because these mirrors need to be so smooth, if the mirror were enlarged to the size of Colorado, the largest bump would be a mere 1 centimeter high. Most clusters in the universe are relaxed. They look like this system over here called the Bell 85. They're often very round, quite round. You see that here. They're denser and X-ray brighter at their center. These centers often coincide with a bright central galaxy. You see that here. The central galaxy sits right down here at the brightest X-ray spot. Even if they're round and isolated, these clusters are changing. One change are mergers, and you see that example here. This is a small group merging in and falling into this bigger system called the Bell 85. The galaxy here lies at the center at this peak right here for this merging group. But also, just because we see the X-rays, we know the gas is losing energy, and we must expect the gas to cool and most likely to form new young stars. So why are these clusters not cool? Many clusters have these bright gas peaks. You saw that in the previous figure. And quantitatively here, you see a graph of brightness plotted vertically with the projection on the sky in the 2 dimensions in the plane here. Some clusters do not show these peaks, but many do. The hot gas is radiating. The gas must cool unless it's reheated. So these strong brightness peaks imply that the gas is dense and the cooling times are short. And because they're short, we can compute, and just looking at the X-ray emission, how much matter should be cooling to produce the X-rays we see. And we know that we should expect to see up to 1,000 solar masses per year of gas cooling. The Milky Way forms stars at a mere 3 solar masses, so 1,000 solar masses per year is quite something to see or to miss. Clusters are old, so we should expect enormous amounts of matter to have been collected, or we should be seeing many new stars. But these large amounts of cool gas were never detected, and very few young new stars were ever seen. For nearly 25 years, this remained a puzzle, a true mystery. Around 2000, supermassive black holes came to the rescue. Not only should there be cooling in clusters, but in the numerical simulations that formed that people used to study the formation of galaxies, too many stars were formed. The galaxies were not quite right. There needed to be a mechanism both to halt and slow star formation while the galaxies were forming, as well as to provide heat in the galaxy clusters that we've been looking at. And what was found starting around 1998 was that all massive galaxies seem to have supermassive black holes at their centers. And you see a schematic of that idea here, that as the bulge or the galaxy mass increases along this axis, the mass of a black hole grows along this axis. There was found to be a correlation: more massive galaxies, more massive supermassive black holes. And it was a supermassive black hole that people used to model and to show that these supermassive black holes could moderate the growth of the galaxy and the formation of new stars. And in galaxy clusters, the black holes were able to inject energy through jets, which also then serves to heat the gas. And you see one of the first studies of that here, where the supermassive black hole was studied to show how it could keep the gas hot in the center of the Perseus cluster, the brightest cluster, X-ray cluster in the sky. And what you see here is that the central region of this cluster is not smooth and even, but it's actually been disturbed. And you can see the contours, these black lines show the regions where there are relativistic particles, very energetic particles, coming from the supermassive black holes sitting here at the peak that fill these cavities and serve to provide extra energy to the cooling gas. So how do the black holes inject energy? How do they blow cosmic bubbles? And what they do is they have outbursts. Supermassive black holes drive energy out into the surrounding gas. How do they do this exactly? Here you see a supermassive black hole in several time steps, starting at the beginning. And near the beginning, there are magnetic fields, lines of magnetic field that connect the supermassive black hole or the accretion disk that surrounds the supermassive black hole, that connect the black hole and the accretion disk to the outside medium. As this black hole spins, as the accretion disk spins, this spinning, this winding, twists up the magnetic field as though you're winding up a spring. And as it wraps and wraps and wraps, it generates more and more pressure, more and more force pushing on the outside medium. And eventually, as this force gets strong enough and powerful enough, it actually pushes and drives the ceiling away, and a jet is formed. These are mechanically powerful systems that then can expel particles and form these beautiful jets that we'll see more of in a minute. From that same work, which described how these jets can form and from the supermassive black holes, there's actually a wonderful movie that you can see here at this address if you want to see the full movie. But here, I will show you the movie, and you can see two projections. This is a vertical slice, and here's the horizontal slice. And you can see the spinning of the material in the disk. And this is a cut perpendicular to the disk. You can see the disk here as material is flowing along the disk. This is the outer part of the accretion disk, and this is the very inner part as material approaches the black hole. Again, you can see the spinning of the accretion disk. This is the other direction. You can see material being forced out just along the inner edge of the accretion disk. And you can see here the formation of the jet, and finally the formation of a very quite nice, beautiful, powerful jet driving energetic particles perpendicular to the disk into the outside medium. What do these jet outbursts do to real galaxies and clusters? The three figures here show a family of dark matter halos from small to large, from individual bright galaxies to very massive clusters. The supermassive black holes power the jets that expel the relativistic plasma into the surrounding gas that we see in the X-rays. Essentially, black holes are blowing cosmic bubbles, just like the picture down here. So you see here in this galaxy, you see two smaller bubbles here, you see another pair of bubbles here, and there's even a third pair on the outside. In this core of a cluster, in the core of the Perseus cluster, you see one nice bubble here, a second bubble here, you see a third bubble here that's now flattened. The bubble started out round, it's been rising in the atmosphere in this direction, and it's flattened. It looks a bit more like a pancake. And in this cluster, this is one of the largest outbursts. You see in blue, the X-ray emitting gas, and you see in red, the relativistic plasma originally coming from the supermassive black hole. The supermassive black hole jets, blue bubbles. The bubbles have now risen buoyantly in the atmosphere. You can see one here, you see the depression, a little bit darker region here, darker from the blue is avoiding this region, filled with the red radioplasma, and you see the same thing down here on the other side. These outbursts are incredibly powerful. You can figure out the energy from these outbursts from the volume of gas, of X-ray gas that's displaced, the size of the bubbles. And you can see these are huge numbers, 10 to the 56 up to 10 to the 62. And for comparison, you can take the sun. The energy output of our sun in 1 year is a mere 10 to the 41, many, many orders of magnitude smaller than what these supermassive black holes have been producing in a second. Let's look at one of these systems, my favorite, in more detail, M87. This is a beautiful image made with the Rosat Observatory many years ago, with a very, very large field of view. You can see the X-ray emission in blue from the whole Virgo cluster. You see many individual galaxies here. They're all labeled. The zoom in to this region shows you the central region where the galaxy M87 sits, right at the peak of the region here. M87, this optical galaxy, is the central dominant galaxy of the Virgo cluster. Relatively nearby, 50 million light years. The black hole sitting at the center of M87 is about 6 times 10 to the 9, 6 billion solar masses. Because we see the X-ray emission, we know the gas is radiating away its energy and cooling. We should see the newly forming stars from the cooling gas, and we should expect to see about 24 solar masses per year, 8 times that of our own Milky Way. And just as I mentioned before, this cooling gas was never found either as new stars or as collections of cold material. M87 is one of these old reddish stars, reddish galaxies, and often referred to as a red and dead galaxy with no young stars. M87 is special, both because it has a very massive supermassive black hole and because it's quite close by. And it was the first object to be studied with the Event Horizon Telescope. And because of its proximity and its mass, one was able to image the black hole shadow for M87. And I will show you that movie here as we zoom in toward M87. In red, we will see again, this is the radio emission. This is the relativistic plasma created by the supermassive black hole jets and the bubbles. We go in further, we're actually seeing the stars. Going in deeper, you can begin to see the jet. This is the optical jet here. We're going in a little bit further. We can now see the more of the radio jet as we probe deeper and deeper and deeper into the center of the galaxy, all the way to the supermassive black hole. And here you see the image from the Event Horizon Telescope. The papers were published in 2019. Here's this image of this shadow of the supermassive black hole. M87 should be everyone's favorite galaxy. The galaxy is old. It was first cataloged by Messier in 1781, so we know it's at least 240 years old. It has a mean stellar age. If you study the evolution and formation of its stars, the stars are at least about 10 gigayears old. And again, the galaxy is red and dead, so it's not actively forming stars. They're all old and red stars. M87 is very popular. There are about 6,000 papers written about it. So it's the most popular elliptical galaxy in our observable universe, and it has about 400,000 citations. It's the envy of all astronomers. And it's the only resolved black hole. This is a remarkable image of Chandra's view of M87. These are essentially raw images. This is a Chandra image in low energy X-rays. This is a Chandra image in higher energy X-rays. And this is the optical image of the stars in M87. And all three images are at the same scale. Here you see the X-ray, these arms and these filaments. You can see these beautiful, very, very fine structures. One large arm goes up this way and the other arm goes to the lower right. Here in the middle image, you see what turns out to be a pressure image. Because of Chandra's response and the temperature of the gas, this image in this harder energy band, is higher energy X-rays, turns out to be an image of pressure. And so you can see regions of overpressure, and you see this beautiful, almost perfect circular region. And this ring turns out to be a shock wave. About 12 million years ago, the supermassive black hole down at the center of M87, had an outburst. It drove bubbles, and it drove the bubble very, very rapidly and pushed a shock wave out into the gas, into the thermal hot X-ray gas. And you see that now as a shock wave that's moving outward away from the center of the galaxy. How to inflate the bubbles? The supermassive black hole drives the jet. We saw how those are formed. And here you see the jet at all different wavelengths. You see the radio jet here. You see the jet from the Hubble Space Telescope, and you see the Chandra X-ray Observatory jet here, all to the same scale. So you really do see the jet across all the wavelengths. The jet is made of this relativistic, very, very energetic particles that are accelerated by the supermassive black hole. And this jet then inflates cavities. And you see that nicely here with two matched images. This is Chandra image. This is the hot gas. This is the VLA from the Very Large Array in the radio, which shows you the relativistic particles best. And you can see the jet coming out in radio. You can also see the non-thermal jet coming here, but all the rest of this emission in the X-ray is the hot gas. The jet then fills up one bubble on one side, and there's a counter jet, a jet on the other side. This jet is pointed almost directly at us. This jet is pointed away from us, as it's much harder to see, but it fills up two cavities, one on each side. There's a third little bubble down here, which just fills this little cavity down here. You can just see the X-ray rim over here. These bubbles, as they fill, they then start to rise and they stir the gas, and that stirring motion can then be used to heat the gas. Comparing the larger images, larger scale images of M87 in the radio and in Chandra, one can study the outburst history of M87. Starting from the oldest and going back to the youngest, the two large circular regions you see here in the radio, these are old relativistic particles that came from old bubbles. They started out at the center, they rose to high in the atmosphere. We're looking at M87 from this side over here, and you see two bubbles that have now risen high up in the atmosphere. They started out circular, but they got to be looking more like pancakes, almost overlapping, as you see here in this little sketch. And they're about 100 million years old. A little bit younger is this beautiful torus. You see that over here. On the one side, the torus has been undisturbed. The bubble rose undisturbed. On the other side, the bubble was disturbed, and you only see this arm now. So these were the two bubbles that were a little bit older, about 40 million years. And a little bit younger, you see at 12 million years, you can just see in this image the shock that we saw more clearly in the higher energy X-ray image. And now down at the center, you can see the bubble that's being reinflated now. This bubble was inflated about 12 million, first inflated about 12 million years ago. It was inflated violently. It drove this shock that we now see further out, but the bubble has been sitting here. It hasn't been rising very quickly. It's been refilled now with the jets that you just saw in the previous slide. And eventually these bubbles will start to rise as well. So you can see these different outbursts, different ages. Sometimes the bubbles are all of different sizes. One can even have huge bubbles as well. So what are the fates of these bubbles, and how does its energy transfer to the gas? The rising bubble loses energy, just like a rising cooling cloud. And in its wake, the bubble generates gas motions. And this kinetic energy, this motion of the gas, eventually it converted back to heat, to thermal energy via the motions of the gas. And this serves to heat the cluster gas. And on average, when you look at M87 quantitatively in great detail, you can find that the average energy loss from the rising bubbles balances pretty closely the energy that we see radiated away. And so here you see a sketch of what happens. You inflate the bubble here, and over millions of years, these bubbles rise, and you see here this beautiful torus. And you wonder how such a torus arises. Well, this is just like a smoke ring. You see sometimes atomic explosions that look just the same way. And you can look on YouTube, you can find examples of beautiful smoke rings, and you see such a one here. You create the outburst, you create a bubble. That hot bubble then rises in our atmosphere, and you see this beautiful torus. You're seeing it edge on one half of the torus on this side, one half of the torus over here. Let's go back to our original schematic of a cluster where we now add our rising bubbles. You see down here, just like M87, the supermassive black hole sitting down here in the densest region of the cluster. And you can see it's here schematically inflated, the two bubbles, one on each side from the pair of jets. And clouds are then rising. And as they rise, the gas is flowing around them. And this gas, as it flows, becomes turbulent and is being stirred by the rising bubbles. And as the rising bubbles move upward in the atmosphere, this stirring is then converted back into motions of the gas and then back into heat to keep the gas from cooling and preventing the stars from being formed. But you ask, you see the turbulence behind these rising clouds, but how is the energy spread all the way around the cluster? How is the energy spread across the whole volume of the cluster? And you can see that here. Here's an example of some ducks moving through a pond, and you can see their forward motion, energy from their forward motion is being spread in waves across the surface of the pond. Similarly, there's a class of waves, gravity waves, that are generated by flattened bubbles, the bubbles you saw in the previous images, that those bubbles can then spread the energy very widely throughout the cluster. In some beautiful work done by Kongyao Zhang, he did some simulations to show what this might look like. And here you see a bubble rising in an atmosphere, and you can see these waves, just like the waves that the ducks are generating on the pond. These waves are being generated in the three-dimensional volume of a cluster, spreading the energy very, very widely around throughout the cluster, even though the bubble itself stays within a fairly small volume. The wave energy is spread very widely throughout the cluster core. All of these mechanisms are still pretty hotly debated, so there's not general agreement exactly how all of this works. And it would be nice to get more evidence to prove exactly how this is working. And one way to do that would be to measure the gas velocities around the bubble, behind the bubble, to understand how the energy is being transformed. And presently, it's not possible to directly measure motions in the hot gas. That will be coming in future observatories. But we can resort to indirect measures. You see such a one here. One would like to use a direct measure, radar spectroscopy. That's the best way to get a precise measure of velocity of a car, or using spectroscopy, the direct measure of gas velocity. They're indirect measures, and you can see an example of such a one here. Clearly, when this car had its accident, it was moving more slowly than the one over here. So what kind of indirect measurements can we use in galaxy clusters? Here you see an analogy with looking at a surface of an ocean. Here you see a calm day. Here you see a slightly windy day. And here you see a day with a great storm. And we can estimate the fluid velocity directly from the images. By measuring the brightness fluctuations, essentially the wave height, one can infer that larger fluctuations yield faster motions, and faster motions yield more energy. Quantitatively, the kinetic energy is half of the mass times the velocity squared. So if we could infer the heights and the velocities, we could get an indirect measure of the velocities of the gas. And that was first done using the two brightest X-ray clusters in the sky, the one around M87 and the one in the Perseus cluster. These require very long observations. M87, this observation was a week-long observation. And for the Perseus cluster, this was a 1.4 million second observation, essentially 3 weeks long. And the idea was to measure the deviations from the smooth image that you see, to measure the fluctuations on small scales, and therefore to infer the velocity and the energy in the gas driven by the bubbles. And voila, the basic idea is that the measurements from different regions, the red patches and the blue patches, the red for M87 and the blue for the Perseus cluster, should lie along a line, the heating equals cooling line, which you see here. It's not perfect, but it's pretty close. All of these different patches, different regions of the cluster, where the cooling is small to where the cooling is large, match what one computes as the heating rate from larger and smaller fluctuations. Again, this measurement is indirect. There are assumptions about the turbulence that are made, and the real proof will await the next generation of X-ray observatories to get the really direct measurements that really would confirm how all of this is really occurring. So let's summarize. The feedback is like baseball. The galaxy cluster is like a baseball team. The batter is a supermassive black hole. Sometimes the batter hits the ball. We never quite know when we're going to have a really exciting game. The jets inflate bubbles. We never know what's going to create an outburst from the supermassive black hole. We don't really know the triggers. There are different sizes of outbursts, just as there are different sizes of walks, singles, and home runs. The pitcher provides the ball, the fuel, the cooling gas for accretion. The hot X-ray emitting gas, those are the fielders. They capture the supermassive black hole output. The fielders are critical. No fielders, no gas, no energy capture, and no feedback. Here you see this, yes, this is the Boston Red Sox. So in the study of the formation and evolution of clusters, we've had enormous progress. There's general agreement that the supermassive black holes are key to the feedback process. The detailed physics is still debated. The shocks and bubbles are likely important. Coming next will be the direct measures of the gas velocity. There are new missions planned. GRISM in 2022 with moderate angular resolution. Athena is coming in the 2030s with another mission possibly still under study with NASA called LINX. And all these missions will bring the next revolution in really understanding galaxies, groups, and clusters, including probing to even earlier times. Returning to my own time here at Smithsonian, I've been lucky to be at this very special place and at this very special time. Just as I began my thesis in 1970, Uhuru, the first mission devoted to X-ray astronomy, was launched. It gave us the first deep look at the sky in a new wavelength, ideal for massive energetic objects, from black holes to galaxy clusters. And here you see the final catalog to which I was able to contribute. It was published in 1978. Just as a side note, Uhuru was launched off the coast of Kenya on December 12, 1970, and it was named Uhuru, Freedom in Swahili, to celebrate the 7th anniversary of Kenyan independence on December 12, 1970. There's also an engineering model of Uhuru, which is sometimes shown at the National Air and Space Museum. I was lucky to be here at this special place and special time. The Einstein Observatory was launched in November 1978, and it was the first fully imaging X-ray observatory. It had a few arcseconds angular resolution comparable to radio and optical observations. At Smithsonian, we both planned and analyzed the observations, and this mission brought X-ray astronomy to the entire international community with a guest observer program to which anyone could apply. Christine Jones, my wife, and I were responsible for processing the data. And we were the first to see the images of many new classes of objects, including clusters. This was you can imagine this was just an incredibly exciting time to be the first to see one object after another. My luck continued. In 1999, the Chandra Observatory was launched, which realized the goal that Riccardo Giacconi had set in the 1960s. For all of this research in X-ray astronomy, he was awarded the 2002 Nobel Prize. Chandra was operated from Smithsonian, and it's the only major NASA observatory operated away from a NASA center. So for me, maybe it's been not just completely luck. Luck is the residue of design. It's a nice quote from Branch Rickey. And so perhaps while it's not been completely designed, at least I feel that I've been here and have been able to make really exciting and good choices. In the past 50 years, starting from Uhuru, you see again the sky map here. The 4U catalog had 339 X-ray sources. About 40 of these were galaxy clusters. And here you see the first sky survey, the first 6-month survey, first of 8, from the eRosita satellite. The average exposure that you see here is about 180 seconds, and there are about 1.1 million sources have been detected so far. Now, 2% of these are clusters of galaxies, and while that's a small fraction, because there's so many sources, the total number of galaxy clusters is now 20,000. So we've come quite a way from our 40 galaxy clusters to now 20,000. Most of the sources are supermassive black holes, and there's a significant contribution of compact stars, pulsars, black holes, as well as diffuse emission from our own galaxy, you see here in the beautiful yellow colors. For me, astronomy has always been a family affair. With many friends and colleagues at CFA and around the world, there's been an incredibly productive and scientific environment at SAO and CFA. And my 3 children, when they were young, often came to work as well. And before our children, even our dog came to work. The figure here you see is an author cloud. whose names of authors proportional to the number of papers that I've co-authored with them. My closest collaborator for almost 50 years has been Christine Jones, and together we've written 346 papers together with our many friends. And I want to thank not just my scientific family, which has been a big one. I want to thank everyone who's contributed to making CFA the wonderful place to work, the productive place to work that it has been for the past 50 years. I'd like to thank you for joining this discussion that was recorded on this 21st day of the 21st year of the 21st century. Thank you.
Thank you, Dr. Forman, for that fascinating account of an important aspect of your work. I'd like to thank all of our viewers for watching and to remind Smithsonian staff members that the call for nominations for the 2021 Smithsonian Distinguished Scholar in the Humanities will be issued very shortly. Please watch for it in your email and begin considering now who among your colleagues you might like to put forth as nominees. On behalf of the Smithsonian's broad community of scholars, I'd like to thank Secretary Bunch and all of the administrative team members throughout the institution at all levels whose work allows our research of all kinds to go forward as we aim to achieve a better future for humanity through a more nuanced view of mankind's collective history and a more thorough understanding of the world around us.